In previous lecture, we learn about what is the 1H NMR and the brief introduction of 1H NMR. Then we learn about the spin state of the particular nucleus. So here we are going to see about the same topic, that is the nuclear spin. So the molecules which present in particular solvent which we use for the which we use to dissolution of the NMR, which is DMSO D6. When we dissolve this particular compound, then the molecules are like this, which are randomly disturbed. So the orientation of the molecules, the direction of dipole moment is the very disturbed. Uh, so, distribution of nuclear spin is random in absence of external magnetic field. When we apply the external magnetic field, then it causes the nuclear magnetic moment to align the parallel or anti-parallel to the applied field. So here we can clearly see the difference between two images, where this is the image before applied the magnetic field, and this image before after the applied magnetic field. Here we can see the molecules are aligned perfectly, which opposite which are same direction, or some are in opposite direction. So here each nuclear behave like the bar of the magnet. So when we apply the external magnetic field, it position get changed and we get the signals. If the number of neutrons and the number of protons are both are even, then nucleus has no spin. If number of neutron plus the number of proton is odd, then the nucleus has a half integer of spin, that is 1 half 3 by 2 5 by 2. If the number of neutron and the number of proton both are odd, then the nucleus has an integer spin is 1, 2 or 3. So the overall spin, that is I, is important. Quantum mechanics tells us that the nucleus of spin, that is I, will have 2I plus 1 possible orientation. Sometime it is having 2n plus 1. So a nucleus with a spin is 1 half will have two possible orientations. In absence of an external magnetic field, these orientations are of equal energy. If magnetic field is applied, then the energy level splits, and each level is given a magnetic quantum number, that is m. So here in this diagram, which shows the lower energy state to higher energy level state. So lower energy state is plus 1 half, and the higher energy level is minus 1 half. When the nucleus is in magnetic field, the initial population of the energy level are determined by the thermodynamics, as described by the Boltzmann distribution. This is very important, and it means that the lower energy level will contain slightly more nuclei than the higher level, and it is possible to excite this particular nuclei into the higher energy levels with the electromagnetic radiation, and it is possible to excite this nuclei into higher level with the electromagnetic radiation, which gives by the strong magnets the frequency of radiation needed, and it is determined by the difference in the energy between energy levels. So in this slide we are going to learn about the chemical shift. The magnetic field at the nucleus is not equal to the applied magnetic field. Electron around the nucleus shielded it from the applied magnetic field. The difference between the applied magnetic field and the field where the nucleus is termed in a nuclear shielding. When we consider the s electron in molecule, they have spherical symmetry and the circulation in the applied field, producing the magnetic field which opposes the applied field. This means that the applied field strength must be increased for the nucleus to absorb at its transition frequency. This upfield shift is also termed as a diamagnetic shift. So, the electron in p orbital have no spherical symmetry. They produce comparatively large magnetic field at the nucleus, which give a low field shift. The de-shielding is termed paramagnetic shift. In proton or the 1h NMR, p orbital plays no part. There haven't any p orbitals, which is why only a small range of chemical shift, that is 10 ppm, is observed. So in last year you can see the chemical shift values from the range of the 1h NMR is very low, when we can easily see that the effect of s electron on the chemical shift by looking at the substituted methane, that is CH3X or the methyl halide. As the X become increasingly electronegative, so the electron density around the proton decreases and they resonate at the lower field strength, which increases the delta H value. The chemical shift is defined as the nuclear shielding or the applied field. The chemical shift is a function of a nucleus and its environment, and it measured relative to the reference compound. For 1H NMR, reference is usually tetramethyl silane.